Today we learn a new programming language called Scheme. We've learned enough Python already, I think. Well, we'll learn a little bit more before the end of the class. But it's nice to see that all of the ideas you've learned about Python can just apply immediately to another programming language that we can learn in just 1 hour. So we'll learn Scheme, and we'll be working with it for the next couple of weeks. Scheme is a dialect of Lisp. Lisp is the second oldest programming language still used in systems today. So the oldest is Fortran. People use it because systems were written in it that we still have around. But Lisp is still used even to start new projects. People just love it. What are people saying about Lisp? Well, Alan Kay, the inventor of object-oriented programming, says that it's the greatest single programming language ever designed. That is high praise from one of the world's great computer scientists. What else do people say? My favorite sci-fi author says it's the only computer language that is beautiful. And Brian Harvey, the CS instructor extraordinaire who taught 61A for many years, one of the great educators in computer science, once remarked to me this. XKCD had their chance to honor Lisp with this comic. I'll let you read it. Moving on in 3, 2, 1. Here we go. Okay, let's talk about the fundamentals of this programming language. Scheme programs consist of expressions. Expressions only, no more statements. Expressions can be primitive expressions, such as the numbers 2 and 3.3, as well as symbols. Combinations are expressions contained within parentheses. Numbers are self-evaluating, so 2 just evaluates to 2. Symbols are bound to values. And call expressions are combinations where we first put an operator and then 0 or more operands in parentheses. So for example, quotient 10(2) is a call expression, and quotient is a symbol that refers to the operation of dividing. It's the integer division in Scheme. So quotient names Scheme's built-in integer division procedure, and a procedure is in Scheme what we call a function in Python. And this call expression, which looks a little bit different because we've moved the operator inside the parentheses, but otherwise has many of the same properties as the one in Python, tells Scheme to divide 10 by 2. And since a combination has other expressions within it, which may themselves be combinations, we can nest in order to get the quotient of dividing the sum of 8 and 7, which is 15, divided by 5 is 3. And just as we can nest things arbitrarily deeply in Python, we can do that in Scheme as well. There's a bit of a convention about how to indent Scheme. So unlike Python, you can use indentation any way you want, and it doesn't matter for the evaluation of the program. I can put my whole program on one line if I want to. Combinations can span multiple lines though, and they often do, just to improve the readability of the program for other humans. So what happens in this particular layout is that we're putting the 2 different operands for the call expression that starts with the plus operator on 2 lines that are indented equally. So we're going to sum together the result of evaluating these 2 sub-expressions. The first operand multiplies 3 by whatever that sum is. That sum is 8 plus 8 is 16. 16 times 3 is 48. And what do we add that to? Well, the sum of subtracting 7 from 10 is 3. Add 6 to that is 9. And the whole thing gives you back 57. Okay, so let's actually look at this. Here's Scheme. I can write the number 1. I can add together 1 and 2. I can even add together 1, 2, 3, 4, and 5. all in one expression. So that's the convenience of call expressions, is that they can take multiple different operands, and we don't need a separate notion for plus versus sum. We just put in different numbers of arguments. We can even add nothing and get 0. What do you think you get when you multiply nothing? 1. The multiplicative identity. What else can we do? Well, we can subtract 3 from 10. We can also just subtract 10. And notice the different behavior there. And finally, what happens when I subtract from 10, 1, 2, 3, 4, and 5? Well, then I get negative 5. So it subtracts all of these different arguments from the first argument. These sum up to 15.